Dear students, now we are discussing about session number 13 for the aberration chapter of BSc program 3rd semester physics of Rani Chennamma University. Let us have the recap of the previous class where we have studied already what is chromatic aberrations, circle of least confusion, lateral and longitudinal chromatic aberration, and the process of removal chromatic aberration as achromatism. During this session 13, achromatism in thin lenses in contact you are going to study. As you know that achromatism is the method to reduce chromatic aberration. The combination of suitable convex and concave lenses which removes the chromatic aberration is called as achromatic combination, and the process of removing the chromatic aberration is called as achromatism. Here if you consider the convex lens and the concave lens individually, they are going to produce definitely the chromatic aberration. So if you consider a convex lens and for a parallel incident rays, after refraction through the lens, they are going to meet at different positions. That is, chromatic means for violet and red light will be separated due to change in refractive index of the lens. Then violet rays are going to meet at FP and red lines going to meet at FR position as shown in the figure. Similarly, when you consider concave lens, here also you are going to have FR and FV which are assumed to be meet at different positions. So, separately convex and concave lenses have chromatic aberration as in the above figure, but when they are joined together there will be reduction of chromatic aberration. The combination of suitable convex and concave lenses which removes the chromatic aberration is known as achromatic combination, and the process of removal of chromatic aberration is called as achromatism. Here we are going to represent this achromatism for lenses, that is in two thin lenses which are in contact. One is concave and another is convex. The combination of these two lenses is such that the effect of one can be reduced by the other. So we can get a single image for a object. Then a white light is passed, parallel incident ray is passed to the combination, the two lenses, one is convex and another concave, in contact, and they are going to focus at a single point F. The condition for achromatism of two thin lenses in contact is given by, for a thin lens its focal length is given by, as you know, 1 by F is equal to product of mu minus 1 and 1 by R1 plus 1 by R2. Differentiating this equation, we get minus df by f square is equal to d mu into bracket 1 by R1 plus 1 by R2. In place of 1 by R1 plus 1 by R2 from the above equation, you can replace 1 by f into mu minus 1 into d mu. Therefore, the above equation becomes minus df by f equal to d mu by mu minus 1 equal to omega, which is the dispersive power, omega equal to minus df by f. For two thin lenses with focal lengths f1 and f2 kept in contact to form a chromatic combination, the equivalent focal length will be given by 1 by f equal to 1 by f1 plus 1 by f2. Let us differentiate this equation. We get minus df divided by f square, which is equal to minus df1 by f1 square minus df2 by f2 square. For achromatism, there is no change in focal length for the colors. That is df equal to 0, which implies from the previous equation minus df1 by f1 square minus df2 by f2 square equal to 0. Replacing omega 1 and omega 2 from the equations minus df1 by f1 and minus df2 by f2, the above equation becomes omega 1 by f1 plus omega 2 by f2 equal to 0, or omega 1 by omega 2 equal to minus f1 by f2, which is required condition for achromatism. Please remember this equation. The condition for achromatism is omega 1 by omega 2 is equal to minus f1 by f2. From this condition, we have the ratio of omega 1 and omega 2 must be same as that of focal length. Since omega 1 and omega 2 are positive, then f1 and f2 must have opposite signs. If one lens is concave, another should be convex. If two lenses are made of same material, then omega 1 equal to omega 2 and f1 is equal to minus f2. So, replacing this, we get 1 by f equal to 1 by f1 minus 1 by f2, which is equal to 0, which implies f is equal to infinite. That is, f is focal length at infinite distance. So, the surfaces of lenses in contact should have the same radii of curvature. At the end of this session, you are able to answer the achromatism, dispersive power, radius of curvature, convex and concave lenses, achromatic combination, focal length and equivalent focal length. So, you can answer some of the multiple choice questions given at the end of this session. Please go through them, and if you want to have more glance on this topic, you can refer the following textbooks. Thank you.